Imagine being able to weigh something huge, like the Himalayas,
Right.
but not with, scales or anything obvious. With atoms.
It sounds like science fiction, doesn't it?
Totally. But Jason Hyon over at JPL actually said, we could determine the mass of the Himalayas using atoms. And, well, that's what we're diving into today.
Yeah, we're looking at a really fascinating, groundbreaking NASA mission. It's called the Quantum Gravity Gradiometer Pathfinder.
QGGPf for short, I guess.
Exactly, QGGPf. And it's set to be the world's first space-based quantum gravity sensor. It could, well, change how we see gravity and our planet, too.
So the mission for everyone listening, and you're already doing it, is to get your head around how this tech works and maybe more importantly, why it's such a big deal for watching Earth and maybe even looking further out.
Definitely. Expect some surprising stuff. The potential is huge.
And just so everyone knows, we're basing this on the info released about QGGPf,
Oh,
including those cool quotes from Jason Hine, Shengwei Chao, and Ben Stray at JPL.
That's right.
Okay, so let's get into it. What's the basic point of QGGPf? What's it trying to do?
Okay, so at its core, QGGPf is all about sensitivity, getting way, way better at detecting tiny, tiny changes in Earth's gravity.
Tiny changes in gravity. Why does that matter so much?
Well, those little variations, they tell you a lot about what's hidden underground.
Ah, right, like where water might be stored,
Yeah.
big underground aquifers.
Exactly that. Or where you might find mineral deposits, maybe even oil and gas reserves.
Because those things have different densities than the rock around them.
Precisely. Different density means a slightly different gravitational pull. And if you can map those differences super accurately,
You get a much better picture of where these resources are, like tracking freshwater supplies globally, which is pretty critical.
it's hugely important. And the way QGGPF plans to do this is really different from how we've done it before.
Okay, how so? What's the old way versus this new way?
So typically, measuring gravity precisely from space has meant using multiple satellites, like working together in formation. Think GRACE and GRACE-O missions.
Right, I remember those. Constellations of spacecraft.
Yeah, but QGGPF, it's designed as a single spacecraft, and it's compact. We're talking roughly 0.25 cubic meter.
Wait, like the size of a small washing machine?
Pretty much. And only about 125 kilograms. So much smaller, lighter, and hopefully less complex than needing multiple satellites.
Wow, okay. A single, relatively small box aiming to do better than a whole fleet. How? What's the magic ingredient?
The magic is quantum. That's the Q in QGGPF. The tech uses two separate clouds of rubidium atoms.
Rubidium atoms, okay.
These atoms are cooled down, way down, to temperatures just a tiny fraction above absolute zero.
Whoa, near absolute zero in space.
Yep. And when they get that cold, things get weird. They start acting less like tiny balls and more like waves. Quantum mechanics takes over.
Atoms behaving like waves. That's pretty mind-bending. So how does that wave-like behavior help measure gravity bar?
Okay, so this is the gravity gradiometry part. The instrument tracks the acceleration of these two atom clouds very precisely as they fall inside the spacecraft.
They're in free fall.
Essentially, yes.
Yeah.
And because the two clouds are in slightly different positions?
They'll feel a slightly different gravitational pull from Earth below.
Exactly. Even a tiny distance apart means a minutely different force. The instrument measures the difference in their acceleration. That difference tells you about the local gravity gradient.
So it's like dropping two identical things very close together and seeing if one falls just a tiny bit faster than the other.
That's a great way to put it. Jason Hyon described it just like that. Gravity gradiometers track how fast an object in one location falls compared to an object falling just a short distance away.
And using atoms means your objects are perfectly identical, right?
Perfectly identical and incredibly stable. That's the quantum advantage. You get this super consistent reference.
Right. I remember Shengwei Chao making that point about stability.
He did. He said, with atoms, I can guarantee that every measurement will be the same. We are less sensitive to environmental effects.
So they're less easily disturbed by, like, temperature changes or vibrations on the spacecraft?
Much less sensitive. That inherent stability is key. Classical instruments can get noisy, but these quantum systems are more robust. That's how they think they can get potentially 10 times the sensitivity of current methods.
10 times.
Yeah.
That's a huge leap. It really could change the game for resource mapping and Earth science.
It really could. We're
Yeah.
basically using the fundamental nature of atoms themselves to make these incredibly fine measurements.
Okay, so this sounds amazing, but also really complex. What's the timeline? When do we actually get to see this thing fly?
Well, the plan right now is for launch near the end of this decade, so still a few years away.
Understandable. It takes time to build and test something this novel.
Definitely. There's a lot of complex engineering, development, testing, making sure it can survive launch and work reliably in space.
And it's not just about proving this one instrument works, is it? I gather there's a bigger picture for quantum tech in space.
Absolutely right. QGGPf has sort of a dual purpose. Goal 1, prove quantum gravity gradiometry works in space. Validate the tech.
Okay.
Goal 2, act as a pathfinder. Push the whole field of quantum sensing forward. Ben Stray put it really well. He said basically, no one has tried to fly one of these instruments yet.
Right. You need to actually fly it to see how it performs.
Exactly. He said, we need to fly it so that we can figure out how well it will operate, and that will allow us to not only advance the quantum gravity gradiometer, but also quantum technology in general.
So it's a stepping stone. Learning from this mission helps develop future quantum devices for space.
Precisely. It's a crucial step for unlocking all sorts of potential quantum applications.
And building something like this, it sounds like it needs a team effort. It's not just JPL.
Bro, absolutely. Collaboration is key here. JPL is working very closely with companies like AOSense and Inflection.
What are they bringing to the table?
They're specialists in the sensor head technology itself, the really core quantum part.
Ah, the atom trapping bits.
Kinda, yeah. And then there's NASA's Goddard Space Flight Center working with Vector Atomic.
And their role?
They're developing the super precise laser and optical system needed to, manipulate and measure those cold atoms.
Wow. So you need experts in quantum physics, lasers, optics, space systems engineering.
All working together. Plus, think about the challenge you raised earlier, cooling things to near absolute zero in space.
Yeah.
That's a huge engineering feat in itself.
Yeah, that really puts the complexity into perspective. Okay, let's shift focus a bit, maybe look beyond Earth. Could this QGGPf technology help us explore other planets too?
Oh, definitely. That's one of the really exciting long-term prospects. The kind of detailed gravity mapping QGGPf is aiming for could be revolutionary for planetary science.
How so? What could we learn about, say, Mars or the Moon?
Imagine mapping the subsurface structure of the Moon or Mars in much higher detail than we can now.
So looking for lava tubes, maybe buried ice deposits?
Exactly. Or understanding the internal structure, the crust thickness variations. On icy moons like Europa or Enceladus, you might even map variations that hint at subsurface oceans or geology.
Wow. So you could potentially find hidden water reserves or understand geological history better.
Yes, potentially gain huge insights into how these bodies formed, how they evolved, what's going on beneath the surface we see. It ties back to that initial idea weighing mountains, or in this case, seeing density variations underground. It's a new way to probe beneath the surface.
So this little quantum box isn't just for Earth observation. It could unlock secrets hidden deep inside other worlds too.
Yeah,
that's pretty amazing.
it really is. It shows how powerful quantum sensing could become, taking these incredibly sensitive lab techniques and making them work out there in space.
It feels like a real convergence, doesn't it? Cutting edge physics, really clever engineering, different groups working together.
Absolutely. QGGPf is pushing boundaries on multiple fronts.
Right.
It's about observing our planet better, yes, but also about expanding our toolkit for exploring the entire cosmos.
Okay, so let's kind of wrap up our deep dive here. We've seen QGGPf is aiming for this huge jump in measuring gravity.
A monumental leap, really.
Using quantum mechanics, these ultra-cold atoms, to get precision we've never had before from space.
Right, giving us this powerful new tool to study Earth systems, water, geology, resources.
And potentially looking further out to understand the hidden structures and histories of other planets and moons in our solar system.
It really opens up a lot of possibilities.
Which brings us to a final thought to leave everyone with. If we can map gravity with this kind of crazy precision,
Yeah.
what are we going to find? What undiscovered resources are down there? What weird geological features might show up on Earth or even, say, Mars?
And how might seeing that hidden structure fundamentally change how we think about how planets work? Could we discover processes we don't even imagine right now?
Something to think about. What secrets are waiting just beneath the surface?